if we want to look at total internal reflection, we got to recognize that total internal reflection will only happen in one of these two cases. In the first case, we got a ray of light going from air to glass, from a low index of refraction to a high index of refraction. And in the second one, we got it going from glass to air, from a high index of refraction to a low index of refraction. If it's going to happen, it might not happen in either case here, right? But if it's going to happen, which one does it have a possibility of happening in? First one or the second one? Low to high index or high to low index? High to low, yeah. If we look at from low to high index, index of refraction goes up, right? As n goes up, we're going to find that v goes down, so does lambda go down, and so does theta go down. If theta goes down, if the angle of refraction is smaller than the angle of incidence, it doesn't matter how big the angle of incidence is, we can never have an angle of refraction that's 90 degrees or more. So it's never going to happen here, no matter what. No matter how big we make that angle of incidence, the angle of refraction will still be less than 90 degrees, and we can't get total internal reflection. It will never happen. But in this case over here, doesn't necessarily mean it's going to happen. My angle of incidence is a certain value right here. My angle of refraction is a certain value right here. It still refracts, but the angle of refraction is bigger than the angle of incidence. As n goes down, theta goes up, which at least leaves open the possibility, if we make our angle of incidence big enough, for reflection to take place. Let's make my angle of incidence a little bit bigger. If I do that, then my angle of refraction might actually be 90 degrees. That's when total internal reflection begins to occur. If we make my angle of incidence even bigger, what's going to happen now? What's going to happen now? It's going to reflect. We haven't talked about this yet, but do you know what the relationship between this angle and this angle is? It's the same. We learned about that in Physics 20, right? The angle of incidence will equal the angle of reflection. We'll talk about that a little bit more in Physics 30 later, next week as well. And so if reflection is going to take place, it's going to take place when you're going from a high index of refraction to a low index of refraction, and if the angle of incidence is bigger than that critical angle. Now, if we look at this, let's get rid of the green, actually, just to make it a little bit less cluttered. Okay, there we go. If we look at this, and we want to find a critical angle from this, how are we going to do it? I'm starting you off here. Sine theta 1 over sine theta 2 is equal to n2 over n1. What do we got to do? What do we got to do to find theta c here, the critical angle? Yep. Why are we crossing sine theta 2 off? You're right, but why are we crossing sine theta 2 off? Yeah, sine 90 is equal to 1, and that's what we make theta 2 equal to, right? Is 90 degrees, because when total internal reflection begins to occur, theta 2 is equal to 90 degrees. Sine 90 is equal to 1, so it becomes sine theta 1 or sine theta c is equal to n2 over n1. We'll rearrange that. Theta c is equal to the inverse sine of n2 over n1. Now, try to get these indices of refraction correct. But I don't know, for whatever reason, when we're doing total internal reflection problems, it's sometimes a little bit tricky. We sometimes get those mixed up. The good news is, if we do get them mixed up, our calculator is going to give us an error, so we're going to know that we get them mixed up. We're not going to have two options on a test and get them backwards and pick the wrong option because we've got them backwards in our calculator. Our calculator would tell us we've done it wrong, so we just switch them around and do it right. Okay, we had 3 questions for homework. We had worksheet number 17, questions 9 to 11. Let's take a look at all 3 of these. Okay, determine the critical angle for crown glass. Well, the index of refraction of crown glass is 1.52. Now, we're solving this question. We have to assume that the other medium is air. Okay, if we're looking for the index of refraction between, let's say, water and crown glass, we're going to have to specify that. If it doesn't specify, it's pretty safe to assume that the other medium is air. Now, are we going from crown glass to air or from air to crown glass? Jane, is it glass to air or air to glass? If we're going from air to glass, air is an index of refraction of 1.00. Glass is 1.52. If we're going from air to glass, then we're going from low index of refraction to high index. We have no chance of total internal reflection taking place. We're going from low to high, right? As we're going from low to high, index increases, theta decreases. We need theta 2 to be bigger than theta 1, not smaller. So it's got to be going the other way around, right? Let's say sine theta 1 or sine theta c over sine theta 2 or sine 90 is equal to n2 over n1. Theta c is equal to the inverse sine of n2 over n1. Now, the good news is, you got those mixed up, you would have had n1, essentially it would have been n1 over n2, and your calculator would have given you an error there, right? So you would have caught that mistake eventually, you just would have done a little bit more work before you caught it, that's all. So let's say the inverse sine of n2 is 1.52 over n1, which is, whoops, my diagram's backwards, right? Because according to what you had said, it's going to be going from glass to air. It's going to be 1.00 over 1.52. Listen, if we're going the inverse sine of something, we're going to be going the inverse sine of a decimal number. So we want the smaller number to be on the top. Right? That's another way to remember it is the smaller number always has to be on the top there. Otherwise, we're going to get an error. When we do that, the inverse sine of that ends up being 41.1 degrees. Now, we'll do the same thing for question number 10 and question number 11, but we'll go through all three of them just because I want to demonstrate something with regard to the answers here. Sine theta c is equal to n2 over n1 again. Theta c is equal to the inverse sine of n2 over n1. Zircon has an index of refraction of 1.92. Is N2 going to be 1.92 or is it going to be 1.00? We've got to be going from high to low index of refraction. So N2 is going to be the smaller value, which means it's going to be 1.00. The inverse sine of 1.00 over 1.92. When we do that one, we end up getting 31.4 degrees. So we get a smaller critical angle here. And finally, when we're doing diamond, we're going to say theta c is equal to the inverse sine of n2 over n1, which is the inverse sine. What's it going to be? N2 has got to be the smaller one, right? We're going from diamond to air, so N2 is going to be 1.00 divided by 2.42. And that's going to give me a value of 24.4 degrees. Now, here's what I wanted to point out to you about this. We talked about this a little bit yesterday when we showed you that picture of the diamond and explained why the diamond sparkled so much. Right? The critical angle of diamond is so small. With a small critical angle, we get more reflection taking place inside it, and with more reflection taking place inside it, we get more sparkling, and that's one of the reasons why diamonds are so valuable. There's lots of reasons, but that's one of the reasons why diamonds are so valuable. We said yesterday that the bigger the difference in the index of refraction, the smaller the critical angle, and therefore the more reflection will take place. If we look at these three questions, you can see three comparisons here, right? In the first one, it's 1 to 1.52. There's a difference in index of 0.52. And then it's 1 to 1.92. There's a difference of 0.92. And in the third one with diamond, there's a difference of 1.42. Which one has the smallest critical angle? The one with the biggest difference in index of refraction. Which one has the biggest critical angle? The one with the smallest difference in critical angle. Does that make sense? It's bigger, not the bigger the critical angle, sorry, not the bigger the index of refraction, but the bigger the difference in index of refraction, the smaller the critical angle, and the more chance we have of getting total internal reflection because, well, it's easier to exceed. It's easier to be bigger than a small critical angle than it is to be bigger than a big critical angle. Okay?